on a little discussion of gases and kind of catch us up. So we just work out 4 different variations of the ideal gas law. I think we got through all of these. Is that right? Did we get through D on the handout as well?
I think so.
I think we did A, B, C, and D, right?
I think we're starting A, because you said something brand new.
Yeah, so number 7 I think was the next one we're going to do. Okay, so as just a little reminder of what we're doing here, let me just bring it up here. So we were talking about gases, obviously. And the last thing we were discussing was the ideal gas law. So PV equals NRT. So just remind me, what are all these little variables? What's P?
Pressure.
Obviously the pressure. V, volume. N, moles. R, yeah, the constant thingy, right? The constant. And T, temperature. Okay, good. So let me just remind you what R is. So R was new last time, and that's 0.08206 liters atmosphere Kelvin. So we said that from now on then, in these kind of problems, all of our other units have to have those same units as R in order for everything to cancel, right? So our volume's got to be in liters, our pressure's got to be in atmospheres, our amount of substance has to be in moles, our temperature has to be in Kelvin, right? So we went through, and those last 4 problems we did were basically all variations on that, where I showed you, like, for example, in the last one we just did, for example, we had pressure, the pressure defined, but the volume was in milliliters, so we had to convert. The amount was in grams, so we had to convert, right? Things like that. So we did several of those. So hopefully that sort of rings a bell, and you've done some of the homework to go back and reinforce it. Have you done some homework? A few of you. Okay, good. Got to do that homework. Regular practice. Okay, so let's just do another little variation here using the ideal gas law in order to find the molar mass of an unknown gas. So this is actually a lab that I've taught before, like at several schools, where you have like a liquid, and you turn it into the gas phase, and then you measure the mass of it, and the volume of it, and the temperature of it, and the pressure, and you can actually find the molar mass of that unknown gas. So we can still use the ideal gas law, PV equals nRT, but now we're going to find the molar mass. So just remind me, what is the molar mass? What are the units typically on molar mass when we find the molar mass of something? When you're adding them up on the periodic table, what's the grams per mole? Yeah. So basically, in order to find molar mass, we're going to look for the grams divided by the moles. Okay, that makes sense? So let's just go through here and read the problem and see what we have and which pieces of the puzzle we are missing. So we have a sample of gas has a mass of 2.244 grams. Its volume is 0.310 liters. Its temperature is 65 degrees Celsius. And its pressure is 924 millimeters mercury. Let's find the molar mass. So let's do our little thing and go through and identify all the different variables we see there. So I see volume, right, 0.310. The temperature is 65 degrees Celsius, so that's our T. Pressure, 924, so that's our P. So in terms of PV equals nRT, which one do we not have? We don't have N, right? We don't have the moles. So we know, though, for molar mass, we need to have the grams, and we got to divide them by the moles. But we do have the grams, right? The grams are given to us right there. So there's a mass of 0.244 grams. So what we can do is we can plug in our P, our V, our T, solve for our moles, and then just divide the grams by the moles, and then we got grams per mole, molar mass. So I'll show you how to do it on this one, and then you guys can try one on your own if we do one here together. So let's look here. So PV equals nRT. You said the missing variable was N, so we know how to rearrange here. We spent some time last time figuring out that. So PV over RT. But again, all of our units have to be the same units as R. So which units here do I have to convert? Which ones are not in the units of the gas constant? Millimeters of mercury, right. The pressure is not in, what should it be in? Atmosphere. So let's do that one first. Good. So the pressure currently is in 924 millimeters of mercury. And you remember the conversion between atmospheres and millimeters of mercury? 760. Yeah, 760. Close. And then, remember, that is exact. That's defined, so we're not concerned with sig figs on that one. So grab your calculator. I see some of you are already punching away. Tell me what you get there. I'll get mine too. 1 point something. What is it? Give me one more sig fig. 1.22. Okay, 1.22 atmospheres. Okay, so that's our pressure. 1.22 atmospheres. How about our volume? What was our volume we marked? Right, 0.310 liters. Okay, good. Our R is the gas constant, so it's constant, so it's always 0.08206. And again, I'll give you this on a test or quiz. You don't need to memorize it, but liters times atmospheres over moles times Kelvin. And then our T, yes, our T needs converted to Kelvin. Right, Lawrence. So let's take that T of 65, and let's add our 273 to it. So what's that give me? 338 Kelvin. Awesome. So, again, as I remind you over and over, make sure you put those units in there so we can cancel them, because that's your safety net, because if they don't cancel, then you know something's wrong and you have to go back and do some more converting. So let's check. Atmospheres, atmospheres. Liters, liters. Kelvin, Kelvin, good. And we're left with moles, which is exactly what we should have because we're finding N. So, looks like 3 sig figs, 3 sig figs, 4 sig figs, 3 sig figs. We're going to have 3 sig figs. So, did you get an answer for moles yet? Let's hear some numbers. What'd you get? 0.0135. Okay, anybody else? Stephanie, did you get that? Same thing? Oh, okay, okay. Same thing. Yeah, the last one's uncertain anyway, so that's okay. 136, 135. Anybody else? Okay, so it sounds like we're getting 0.0136 moles. Okay, so we're almost there, but we want to know the molar mass, which you told me was the grams per mole. So here's my grams, here's my moles. So I can just divide those. So let me clear a little space out here. Do a little erasing real quick. Make a little room here. So our molar mass is going to be the grams. Let's put MM here for molar mass. 0.244 grams per mole, and the moles you just helped me find was 0.0136 moles. So let's see, what's the molar mass of this unknown gas? How many sig figs do you think we should have there? Probably 3. Okay, 17. Awesome. So that's the molar mass. So yes, that kind of helps us narrow down then what possible gas could it be. So some gas that has a molar mass of around 18. So I don't know, maybe it's water. Water's around 18 or something, but something like that. Okay, any questions on that? Again, it's basically real similar to what we spent the last part of the last section on, but now we're just adding one more step. Now we're going to solve for a variable and then use the mass to find the molar mass. Okay, well, your turn. So try B, try it out, help each other out, talk it over. Man, no crystals either, huh? Gonna have to do a few conversions here, as you can tell as you're reading it. Again, it's helpful. Yeah. As you're reading, to go through and label what's P, what's V, what's T, or just make a little list. What's my V, what's my T, what's my P. Then you'll see what's missing.
Same thing.
Wondering.
I needed it.
Help each other out once you get an answer. Talk it over. See if you guys are on the same page. Oh yeah, the molar mass is going to be grams per mole. So yeah, okay, you're right. Yep, you're on the right track. 12. Okay, well let's compare if you haven't yet. See what your neighbor got, help each other out. See what you guys think. You're still finishing up here, but
I got 0.829. Oh,
0.8206. Still seems a little big though. Make sure you're dividing by both of these, right? Because they're both on bottom.
yeah.
Not dividing and then multiplying.
Yeah.
Answer there, Roy? Or? Oh yeah, that's on. I think. Yeah. Yeah. Okay. So yeah, so I see 76.9. A lot of people have that, so that seems to be the consensus. Okay. Well, let's work it out. Good. That's encouraging. It's always nice to have the same thing as everybody else. Hopefully, that's the right thing. So what do we know here? Let's go through and label. That's always handy. So here's our volume. Here's our temperature. Here's our pressure. So now we got PV and T. We're missing N again. So we'll rearrange like last time, and it'll be PV over RT. But again, our units have to be the same as the gas constant units: liters, atmospheres, moles, and Kelvin. So which ones do you have to convert here? The temperature and the pressure, right? Okay, so the temperature, we can do that real quick. So take 85 Celsius and add 273. What's that, 358? Then we'll take our pressure, 783 millimeters mercury, and convert that to atmospheres. And you told me last time 1 atmosphere is 760. So how many atmospheres is that? 1.03, okay. Okay, so let's plug all of that in. So P, 1.03 atmospheres. V, 0.295 liters. R, 0.08206 liter atmospheres per mole Kelvin. And T, we just found 358 Kelvin. Okay, well, always cancel units. That's your safety net. Make sure things converted where it needs to be. Atmospheres, atmospheres, liters, liters, Kelvin, Kelvin. Looks good. We're left with moles, which is what we want. So what'd you get for moles? 0.0103. Okay, so that's the moles, but we want the grams per mole for this one. So we're going to take our grams per mole. So we've got to do one more thing, though, because we don't have grams. We have milligrams. Exactly. So let's take our 792 milligrams. Running out of room here a little bit, but so 1 milligram is 10 to the negative third gram. Yeah, thank you. So 0.792 grams. So there we go. So 0.792 grams per 0.0103 moles. And you said 76.9 grams per mole. Okay, well, if you didn't get that, did you find your mistake? Do you have a question? Okay, I feel pretty good about that. I think we all did pretty well. Exciting. Okay, well, let's move on to one other little way to use the ideal gas law. And now we're going to bring in our friend from the last chapter, stoichiometry. We're going to take some balanced equations now, and we're going to use some gases now, instead of just, solids and molar masses and things like that. So this problem has to deal with drain cleaner. I think this is the reaction that's in the professional strength liquid plumber stuff you buy. But basically, as it says here, so some commercial drain cleaners contain a mixture of sodium hydroxide and aluminum powder. When the mixture is poured down a clogged drain, the following reaction occurs. So sodium hydroxide plus aluminum plus water makes this stuff, and then hydrogen gas. So here's our gas. The heat generated in this reaction helps to melt away obstructions such as grease, and the hydrogen gas release stirs up the solids clogging the drain, bubbles and stuff, and shakes things loose so it can flush down the toilet or down the drain. So it says, if 3.12 grams of aluminum are treated with excess sodium hydroxide, so we got 3.12 grams of this, how much of this could we make at 23 degrees Celsius and 1 atmospheres? So that's kind of a standard temperature and pressure you might have in your bathroom or your kitchen. So let's see what we know here. So let's just go through and do our little labeling trick here. Actually, I'm going to go to I have a little shorthand version of it here. So what do we know here? So we know 3.12 grams of aluminum, right? And it wants to know what is the volume of H2. So I'm going to put question mark over here. I'll put liters volume. What do we have? We got a temperature, and we got a pressure. So I have aluminum, but I want hydrogen. So what do we know now about how to relate two different, Yeah, I mean, molar mass will get us into moles, but how does that relate aluminum to hydrogen? What's that? Yeah, the molar-mole ratio. So we know that for every 2 moles that I put down the toilet, basically, I'm going to get out 3 moles of hydrogen. Are you with me? So if I want to find the volume of hydrogen, well, then I could use the PV equals nRT, because then I have the P, I have the T, and I could find the moles because I can figure out how many grams of aluminum turns into how many moles of aluminum turns into how many moles of hydrogen. And that'll give me the moles, and then I can solve for V. So let me do one of these. So let's figure this out here. So this is a throwback here. So if I had 3.12 grams of aluminum, what's the first thing you have to do with mass? What was that? Molar mass, yes. The only thing we can do with mass is molar mass. So grab your periodic table there. Look up aluminum. I think it's 26.98. Yeah, thank you, sir. Awesome. So that's 1 mole of aluminum. Okay, so grams canceled. But I don't want aluminum. I want hydrogen. So how do I relate aluminum to hydrogen? Mole to mole ratio, right, which is what for this balanced equation? What is it? Yeah, for every 2 moles of aluminum that goes in, we get out 3 moles of hydrogen. Perfect. So 2 moles of aluminum gives us 3 moles of hydrogen. Okay, so let's see how many moles of hydrogen we get, and that'll be our N. Now, that'll be moles. So let's try that out. 3.12 divided by 26.98. So what'd you get? How many moles? 0.1735, okay? I'm going to mark the third sig fig here. Okay, so now we have N. So there's our N. We got N, P, and T, so we can solve for our V. So let's do that. So PV equals nRT. We want to know what's the volume of that. So what will the equation be? V will be watt over watt. What's the equation rearranged to give me?
V equals nRT over P.
nRT over P, right. Good. Okay, so let's plug all that in. So N we just found was 0.1735 moles. R is our constant. It's always 0.08206 liter atmospheres per mole Kelvin. What's our T?
296 Kelvin.
296, right? 23 plus 273, good. And we divide that by our pressure, which has to be in atmospheres, and it already is. 1.00 atmospheres. So, cancel units, moles, moles, atmospheres, atmospheres, Kelvin, Kelvin. We're left with liters, which makes sense because we want a volume. So let's see. Oops. So what'd you get? 4.21, somebody says? Somebody else? Awesome. Okay. Let's think about that for a second. To me, that's kind of an amazing thing because it says you only reacted 3 grams of aluminum. And you know from the lab, 3 grams of something isn't much, right? I mean, 3 grams is a very little bit, but you get out over 4 liters of gas, right? So that's a lot of gas, right? So 2 liters, more than that. So yeah, it's kind of amazing, right? So a little itty bitty bit of aluminum gives you 4 liters of gas out. So yes, lots of bubbling and percolating and stuff in your clog there going on. Okay, so we're kind of tying things together, right? So we're tying the last chapter now and with this chapter, kind of bringing it all together here. Okay, your turn. Why don't you try number 9? So this is for metabolism of glucose in your body. So it says, here's the reaction. What volume of carbon dioxide would you produce at a body temperature of 37 degrees Celsius, a pressure of 0.970 atmospheres, when you use or you metabolize 24.5 grams of glucose? So 24.5 grams of glucose gives you what volume of this? So try it out, talk it over. See what you get. So you have glucose, you want carbon dioxide. What are you doing first?
Writing
Yeah, finding n. So yeah, you're doing. How are you finding n? Right, the mass of glucose turning into moles of glucose, mole to mole ratio. Looks like most of you are on the right track here. Just find the molar mass there. Just find the molar mass. Oh, I see you're doing right now. Nice, fast. Looks good. What's the units? For volume? Your units cancel. You'll see what's left. Okay, well, help each other out if you haven't yet. Compare. See if you guys agree or give each other a hand if you need to. Looks good. Good. Okay, compare with somebody, please, if you haven't yet. See what you guys got. Talk it over. Talk it over.
Oh,
What did you get? Awesome. Okay, so let's hear some answers. Looks like most of you are getting the same thing, but let's hear it. 21.4 liters, okay. 21.4. Okay, well, let's try it out here. So let's go through and figure out what we know, what we don't know. So I want to know the volume of carbon dioxide. So I'm going to put question mark liters. That's what I want. What do I know? I know the temperature of the gas. I know the pressure of the gas. And I know the mass of the glucose. Let's put that in. 24.5 grams of glucose. I have to take that glucose and I want to turn it into carbon dioxide. Okay, so you're right. You told me the first thing to do was to convert that glucose into carbon dioxide. Right. So let's do that. So what do I do with mass of glucose? What do I do with mass of glucose? Yeah, molar mass, right? So add up 6 carbons, 12 hydrogens, 6 oxygens. I just happen to know that one. I think it's 180.18. Okay, so now I got moles of glucose, but I don't want glucose. I want carbon dioxide. So what's the relationship between those two? Yeah, so for every 6 carbon dioxides, I must have put in 1 glucose, right? 1 mole glucose produces 6 moles of carbon dioxide. Awesome. Okay. So what'd you get for that? How many moles of carbon dioxide did you make? 0.8 what?
1/6. 1/6.
1/6. Okay, thank you. Moles, that's moles. So that's N. There, we found our N. So now we got N, P, and T, so we can find V. So just like last time, V is going to be nRT over P. So N was 0.816 moles, R 0.08206 liters, atmospheres per mole Kelvin. What's our T? Yeah, 37 plus 273, so 310 Kelvin. And our P, 0.970 atmospheres, right? So, okay, well, let's cancel. That'll make sure we have the right units left. Right, Alec? So now we know which unit is left. Oh, liters is left. So what'd you say it was? 21 point. Awesome. So again, think about that. That's a pretty amazing amount of gas, I think. Right? So over 10 2 liters worth of gas when you just burn in your body 24.5 grams of glucose. You're going to breathe out over 10 2 liters of carbon dioxide. All right, so that's a lot of carbon dioxide coming out of there. Okay, well, let's move on here. Any questions on that? I feel like most of you got it just walking around. Looks like you're on track. Okay, so let's try one more little variation here. Same equation, but now let's try 50 grams of glucose and figure out how much oxygen would you have to metabolize that 50 grams of glucose. So similar there, but it should be pretty quick, and then we'll move on here. Okay, wow, you're really fast at this one. Flying through it.
Next week's lab.
Okay, so now we have 50 grams, 50.0 grams of this, and we want to know this one, the oxygen. So we're relating glucose to oxygen this time. So same thing, we've got 50.0 grams of our glucose, C6H12O6. And now you're going to use the molar mass again, turn it into moles. So it's still 180.18. But how do I relate glucose to oxygen?
1 glucose to 6 oxygen.
Exactly, right there from the balanced equation. 1 glucose to 6 oxygens. Perfect. 1 glucose to 6 moles of oxygen. Okay. And how many moles of oxygen was that? 1.67. Okay. So that's our N. Perfect. Okay, well, let's just plug it in real quick. So N, 1.67 moles. Whoops. There we go. R, 0.08206 liter atmosphere per mole Kelvin. T, what's T? 298 Kelvin, yeah, no converting even needed this time. And our P, what's our P? 1.00 atmospheres. Okay. Okay, if it's too noisy out there, you're welcome to close that door if you need to. Okay, so everything cancels but liters, which makes sense because we're finding volume. Yeah, thank you, Stephanie. So what'd you get? 40 point what?
8.
Okay, so again, 50 grams. Burning 50 grams, you got to inhale 22 liters of oxygen, so lots of oxygen. Okay, well, you might remember this gentleman here. Are you breathing again? So, remember this guy, John Dalton? We mentioned him back with the structure of the atom. He came up with this like atomic theory. Remember? We also dealt with some gases and things, and Dalton's law is one of the simpler ones. It's called Dalton's law of partial pressures, and basically what it says is that the total pressure of a mixture of gases is just the sum of each of the individual gases. So you just add them together. So let's say you have air, for example, and air is a mixture of oxygen and nitrogen and carbon dioxide and little bits of argon and things like that. Well, the total pressure of that mixture is just the pressure of the oxygen plus the pressure of the nitrogen plus the pressure of the carbon dioxide, et cetera, et cetera. So that's all that law says, is that your total is just the sum of each of the individual gases in the mixture. And here's a little chart out of your book that I took, and this kind of shows you here for air. So, for example, if nitrogen was 594 millimeters of mercury, pressure of oxygen was 160, all of these were 6, but you just add them together, and then the total pressure is 760. So you just add them right together. So that's Dalton's law. So the individual pressure of each gas, that is a part of the whole, we call that the partial pressure. So this is the partial pressure of the nitrogen, the partial pressure of the oxygen, the partial pressure of carbon dioxide and argon, and things like that. So you put all the parts together and you get the total. Okay? So let's just do one real quick. So let's say you had a sample of gas, and it was nitrogen, oxygen, and carbon dioxide, pretty typical like for air. If the partial pressure of the nitrogen is 587 millimeters of mercury, the oxygen is 158 millimeters of mercury, and the carbon dioxide is 7 millimeters of mercury, what is the total pressure, the barometric pressure of that sample in millimeters of mercury? So what do? Just add them up, yeah. So we're going to take, so the total pressure is going to be the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of the carbon dioxide, right? So let's just add them up here. So 587 plus 158 plus 7 millimeters of mercury. And what'd you get?
752.
752 millimeters of mercury. Okay, well, let's do one slight little variation on that. Maybe, if I can get it there. Okay, so this one here is there on your handout. So this one says you have an anesthetic, and it consists of cyclopropane gas and oxygen gas. So the mixture has a total pressure of 1.09 atmospheres. Well, so out of that total, 73 torr is cyclopropane. So how many torr must oxygen be? And you remember what a torr is? Yeah, 1 atmosphere is also 760 torr, right? A torr is the same as a millimeter of mercury. So 1 atmosphere is 760 torr. So it's saying the total is 1.09 atmospheres. If 73 torr, that's cyclopropane, how much of it must be oxygen? So think about that, talk it over. So you have the total and one of the components. What's the other component have to be? Okay, well, let's talk it over if you haven't yet, you know. How you thinking about it? How you setting it up? See if you guys are on the right track here, or on the same track at least. But it does say in torr. What's the partial pressure in torr?
So Dalton.
Pardon me?
Would you multiply 1.9 times 760?
Yes.
Okay.
Exactly. Okay, so I see a bunch of you getting the answer, or at least a answer. What'd you get here, Lauren?
755.4.
755.4. Sydney's nodding. Daniel's nodding. Okay, good. Okay, well, let's just try it out then. So we have the total is 1.09 atmospheres. So we're going to convert that to torr. Absolutely. 1 atmosphere is 760 torr. So let's see what that gives us. $828 torr. So that's the total, right? So, how do I find the oxygen? Yeah, I'll subtract the cyclopropane. So subtract the 73 from the cyclopropane, C3H6. And how much was left? 755. So that's the torr of the oxygen, right? Okay, well, I'm going to move on. That one's pretty straightforward. Any questions? Just add them up, get the total, right? So that's not bad. Okay, so there's another little picture I took when I was in London a couple years ago doing that little science trip. I remember, you might remember that I mentioned went to this place called the Royal Society where they have all these letters and correspondences of various scientists. So here's a correspondence I actually found between Dalton and another gas guy. See that guy there? Gay-Lussac, remember, in Paris. So writing back and forth about gases and atoms and things like that. So it was kind of cool to see it. So one of the things I kind of noticed was their handwriting was so neat back then, wasn't it? So pretty. It's amazing how nice their handwriting is. So that's kind of crazy. So here again, our buddy Gay-Lussac. Well, Gay-Lussac also dealt with the law of combining volumes. So not only was he doing things with pressures and volumes and temperatures, but he also worked with combining gases. So one thing that Gay-Lussac figured out was kind of interesting. Well, let's say you had a reaction like this. Hydrogen gas plus chlorine gas making hydrogen chloride gas. Well, he figured up then that when the hydrogen and the chlorine gases combined, they always combined in simple whole number ratios. So for example, let's say you put in 10 milliliters of hydrogen gas, well, then it would take 10 milliliters of chlorine gas, and you would get out 20 milliliters of hydrogen chloride gas. So your ratio, well, 10 to 10 to 20 is like 1 to 1 to 2. So it's a simple whole number ratio between the gases. So that 1 to 1 to 2 ratio looks an awful lot like what? Yeah, the mole ratio too, right? So you can see that. So the volumes combine in the same ratio, 1 to 1 to 2, as the moles do, 1 to 1 to 2. So that's really handy. So if you have a system that's under a constant temperature and pressure and things, then you can just say, okay, if I need 5 liters of hydrogen, how much chlorine will I need? Oh, it's 1 to 1, so I must need 5 liters of chlorine, and I must make 10 liters of hydrogen chloride. So the same ratio works for volume and for moles. So you can just pull out those coefficients and use them for moles. So let's just give you a real simple one. So let's just say, I had this reaction, 2 sulfur dioxides plus oxygen makes 2 sulfur trioxides. If I have 38 liters of sulfur dioxide, how many liters of oxygen will I need? And we're assuming again, again that we're not changing pressures and things, so it's just kind of constant. So if I put in 38.0 liters of sulfur dioxide, how many liters of oxygen will I need? 19. Yeah, 19. Why? How do you know that? What's the relationship? 2 to 1, right? Same as the mole ratio. So for every 2 sulfur dioxides, I need 1 oxygen. So it just works the same. So isn't stoichiometry wonderful? It's all coming back for gases now too. So yes, we get we need 19.0 liters of oxygen. Okay, right. Okay, well, how many liters of sulfur trioxide would you make if you put in 38 liters? 38 liters, right? Because it's 2 to 2, right? So those are the same. So 38 goes in here. You could put 2 to 2, and 38 would come out. Right, okay, so that works for the same ratio there. Okay, well, this leads to another little thing called the molar volume. So remember in the last chapter I hounded molar mass and how molar mass, what you use to convert moles to mass and mass to moles. Well, now we have molar volume. We're going to use molar volume as a way to convert moles to volume of a gas and volume back to moles. But molar volume is true at this thing called STP. So oftentimes you will see scientists report things under STP conditions. So that stands for a standard temperature and pressure. And the standard temperature and pressure have been defined to be 0 Celsius, which is 273.15 Kelvin, and 1 atmosphere. So that's STP. When you hear STP, it means the temperature is 0 Celsius, and means the pressure is 1 atmosphere. So make a note of that, STP. That's the standard temperature and pressure. So what you can do then is you can plug these numbers into the ideal gas law. And you could say, okay, so what would the volume be of 1 mole at that temperature and that pressure? So you could just rearrange your equation. V equals nRT, and you could put in, okay, well, it's 1 mole at that temperature and at that pressure. And if you do all that, you need to write this all down if you don't want to. You would figure out, 1 mole under those conditions has a volume of 22.4 liters. 1 mole of the gas under that temperature and that pressure has 22.4 liters. That is called the molar volume. Now, the interesting thing about that is you'll notice it didn't say what the gas was, because it doesn't matter. It could be a mole of oxygen, hydrogen, carbon dioxide, whatever. 1 mole of any gas at that temperature and pressure is going to take up 22.4 liters. So this is a handy thing for us. So you might recall, again, I'm going to go back and draw the little flow chart thing that I drew before with our moles in the middle, but now I'm going to add something on here, molar volume. So before I showed you how moles was the crossroads, and we could go from particles to mole, which was what? How do you go from particles to moles and moles to particles? What did we use? Avogadro's number, yes, good. Avogadro's number. So 6.022 times 10 to the 23rd. And we know we can go from moles to mass. How do we go from moles to mass? Molar mass. Yes, I beat that into your head. We got that down, so we just find out the periodic table. And now we have a new one. We can do moles into volume of a gas. So just like moles to mass is molar mass, moles to volume is molar volume. So we're going to use molar volume now. And that says that 1 mole equals 22.4 liters, with a little caveat, though, again, that that's only at STP. If we're not at STP, then we have to do it the way I showed you before with the equation, and you got to plug in your own T and plug in your own P and find your own volume that way. But if you're at STP, now you have this new thing. So moles is the crossroads, right? That's why it's so important. So you can go from volume of gas, get it to mass, or mass to volume, or volume to particles. We can go all around here as long as we go through that mole crossroads. And we'll add another one here in another chapter or two for volume of solution with molarity. But then we'll have 4 things going through the same crossroads. But for now, we're just building it up. So, okay, so let's just look at this and see how this might help us out. So pull out your hand out there, please, and then we'll look at number 11. What mass of calcium must react with phosphoric acid to release 38.5 milliliters of hydrogen gas? And here's the key, at STP. So whenever you see at STP, you go, oh, ding, ding, ding. That means I can use molar volume. Okay, so at STP means you can use molar volume. So yeah, so underline at STP or something, or highlight it so you remember, aha, this means I can use molar volume. Okay, so let's figure out what we know, what we don't know. So we have 38.5 milliliters of this. Our question is, how many grams of calcium? So let's don't make this harder than it is. I feel like sometimes students are always like, I'm so confused, but I promise it's not that bad.
It's just like 3 to 3.
In the moles, yeah, exactly. So we have 38.5 milliliters of hydrogen. Okay, so let's just erase that for a minute. And let's say I told you it was 38.5 grams of hydrogen. What would you do first? Molar mass, right? 30.5 grams, you say, oh, molar mass. Well, it's not grams, it is a volume. So what are you going to do? Molar volume, right, molar volume.
It's being liters, though.
But exactly. But the only thing is our volume's in milliliters and the molar volume's in liters. So yeah, so let's turn milliliters into liters. So 1 milliliter, what's milli? 10 to the what? Negative third, good. So yeah, so now we're in volume of hydrogen. I want to be in moles. Oh, moles to volume, molar volume. Just like moles to mass is molar mass. So 1 mole of hydrogen is 22.4 liters. Good. Okay, now I'm in moles of hydrogen, but I want to be in calcium. So way over here. So how do I relate hydrogen to calcium? Molar-mole ratio, which is 3 to 3 in this case, right? For every 3 moles of hydrogen, I must have had 3 moles of calcium. Okay, 3 moles of hydrogen, 3 moles of calcium. Good. Now I'm in moles of calcium, but I want to be in what? What's my goal?
Grams.
Mass of calcium. So how do I go moles to mass?
Molar mass.
Molar mass, yeah. So find calcium on your periodic table. I think it's 40.08. Thank you. Okay, good. There you go. So plug that all in. Did you get an answer? Let's hear it. 34.6. Mr. Silent. Okay, 34.6. What? 34.6. What? What's my units? Grams. Good. Okay, so real similar to what we were doing before, right? So again, I'll say it like this way. If that would have been milligrams, you said, oh, mass got to turn into moles. So you'd have done milligrams to grams of molar mass. But it's volume. Oh, molar volume, right? So just the same kind of thing. So it's just knowing which tool to use out of your chemistry tool belt, right? Right? So now you have Avogadro's number, molar mass. Now you have molar volume too. So you have 3 possible different tools you can use to get between there. Question? Oh, you're not getting that number at all? Okay, let's see. Okay, maybe not. Last time I'll trust you guys. No, I'm just kidding. So what'd you get? Did you divide by 3 and 3 and 20.4 and? Okay, well, let me try it out. 38.5. What? Well, I'm glad you said something. Normally you guys don't lead me astray. That's what I got it all either. I got a much smaller number. Okay, well, I'm glad you said something. Thank you. So, what did you get?
0.0689.
That's what I got. Okay. Man, led me astray over here, gentlemen. Can't believe it. You still don't say anything? You just nodded your head. You what? Yeah, whatever you got. Okay. Okay, let's try another one. Try this one. How many milliliters of hydrogen chloride gas now could you make from 25.0 grams of barium chloride? Ding, ding, ding. At STP. So that tells you, aha, I can use that molar volume thing. Try it out. Okay, let's work it out. So we have, let's write what we know, 25.0 grams of this, and I want to know how many milliliters of that. So let's start with what we know, 25.0 grams of barium chloride. So you have mass, what's the only thing you can do? Molar mass, so out of a barium, 2 chlorines, and what is that molar mass? 208.23. Okay, so that gives me mass per mole of barium chloride. Now I'm in moles of barium chloride, but I want to connect that to HCl. How do I connect the two? Mole to mole, which is for every 2 HCl's, I must have had 1 barium chloride. Good. My golly, I smell learning. It's awesome. Okay, now we're in moles of HCl, but I want to be in volume of HCl. So what do? Molar volume, yes. Molar volume. So 1 mole HCl is 22.4 liters. At least it is when you're at STP. Again, if you're not at STP, you got to do a little differently. You just got to solve for the N, then plug it into the PV equals nRT thing like we did earlier. Okay, we're almost there. I'm in liters, but I want to be in milliliters. Yes, so 1 milliliter is 10 to the negative third liters. Sorry for my messy 3 there. And what'd you get? Should have 3 sig figs. So what is it with 3 sig figs? 5,380 milliliters, or 5.38 times 10 to the third. Probably the more preferred way there, so we get rid of those ambiguous zeros at the end. Okay, a little messy, but we're in a hurry here. Okay, any questions on that one? Questions? Okay, so there we go. So So a few little announcements again. So remember, today's the last day to turn in your science fair thing, if you have that to do. So make sure you get that in today. And also next week in lab, if you haven't yet demoed it for me, please bring those setup to me next week in lab. Right. For me then, kind of demo it in class. Make sure it actually works. Make sure as well you also know how to answer questions, for kids in terms of the chemistry behind your experiment on that. And we also have a new experiment, of course, next week. So pre-lab, all that good stuff, like always. And we have finished chapter 7, which means what? On Tuesday. Homework and a quiz. Yes, we'll have a quiz. So write that in your little planner. Have a quiz on chapter 7 on Tuesday. The homework will be due on Tuesday as well. Yes.
So you can do makeup work at any point, right? Like you missed some homework?
Yes. Yeah. Sure can. Yep. Weeks and months later, you can do makeup work. Yeah, you might have missed. Yeah, for half credit still on mastering chemistry. Okay.
Oh, did you figure out that?
Okay. So I guess we're done. Any questions? I know you had one question, but I answered your questions. Okay, we're out a little early. That's shocking. So we'll see you on Tuesday then. If you have any questions, though, stick around and ask me.
So will all the laws be on the book they give it to us, or should we remember?
I will give you the combined gas law and the ideal gas law and the R. And now the combined gas law. Remember PV over T. Yeah, I'll give you the molar volume. I'll give you the molar volume. And I showed you then how you can find the other laws out of the combined gas law. Remember that showing like PV over T, PV over
Just
T.
like kind of.
You gotta hide in the ones you're not using, then you can find the other ones.
Okay.
Right. So
just know how to use them.
yeah, exactly. So I'll give you all the laws, all the constants. You just have to know how to use molar volume, how to use the ideal gas constant, all that stuff.